On the morning of November 17th, 2025, new high-resolution data from both ground-based and orbital observatories confirmed something most astronomers were hoping not to see. 3I-ATLAS isn't falling apart, it's building. What was once considered a fragile interstellar fragment, maybe a volatile-rich comet from a distant star system, has now revealed distinct spatial formations around its core. Not random dust clouds, not disintegration, but structures, linear alignments, geometric segments, reflective arcs that remain stable across imaging passes. This is not what any natural outgassing model predicted. In fact, it defies decades of cometary science. But the most unsettling part is not just the symmetry, it's that the structures are growing. Stay with me as we break down the data from today's release. If you're listening from anywhere on Earth, let me know what time it is where you are. And as always, if you believe science should stay honest, consider subscribing to follow every chapter as this unfolds. Now let's begin. On the morning of November 17th, 2025, a wave of high-resolution data changed the way astronomers talk about 3I-ATLAS. For months, the assumption had been that this interstellar object, travelling at over 30 kilometers per second, was gradually breaking apart as it encountered solar radiation, gravitational stress, and thermal imbalance. That assumption no longer holds. The object's nucleus, or central mass, has shown no signs of fragmentation. More surprisingly, it has remained consistent in shape, volume, reflectivity, and rotational behaviour over the past 7 days, even as it passed through a region of space that should have introduced measurable stress. Multiple observation sources, including the James Webb Space Telescope and the UNNAVE's ground-based array, report zero structural deformation. The light curves are clean, the thermal signature is stable, no new debris clouds have emerged, no brightness dips have occurred that would suggest internal collapse. This contradicts the core physics of what we know about interstellar objects, particularly those with a cometary or ice-rich profile. Any body subjected to solar radiation after spending millions of years in the frozen dark of interstellar space is expected to shed material rapidly. This is the result of sublimation, when frozen volatiles like water, carbon dioxide, or ammonia heat up and explosively convert to gas. The outward pressure this creates is one of the primary reasons cometary nuclei crack or fragment near perihelion. Yet 3I-ATLAS continues to resist this fate. So what does this mean? The most immediate conclusion is that the object is not composed of loosely bound, volatile material. If it were a typical rubble pile, or even a compacted icy core like 2I Borisov, we would expect activity. Instead, we're observing near total inertia. The object's outer layer is intact. There is no sign of crustal collapse or thermal cracking. Its surface albedo, the measure of how much sunlight it reflects, has remained fixed within a margin of 2%. That means not only is it not breaking up, it isn't even flaking. Some scientists suggest this might indicate a metallic or rock-dominated composition. That would make 3I-ATLAS far more similar to asteroid-like bodies than comets, despite early expectations. If it's solid, perhaps composed of iron, nickel, or dense carbon, then it would naturally be more resilient against thermal expansion, internal stress, and gravitational tides. But even this theory doesn't fully explain the extent of stability we're seeing. Solid bodies, especially those that have been exposed to micrometeorite impacts over millions of years in deep space, tend to carry surface fractures and thermal stress points. These don't stay dormant during close solar approaches. Heat causes expansion, and expansion causes breakage. That isn't happening here. Another theory emerging from today's analysis is structural reinforcement. This doesn't necessarily imply anything artificial, but it does suggest that some kind of internal strength or binding is resisting fragmentation. That could be due to chemical cohesion, metallic fusion in the past, or gravitational compression beyond what we expected for an object of this mass and size. But again, even these explanations are theoretical stretches. There is one more possibility, and it's what's generating the most quiet debate behind closed observatory doors. This isn't stability by accident, it's stability by design. If the core of 3I-ATLAS is not only holding together but doing so while orienting its mass in a way that minimizes tidal stress, if it's rotating in a locked pattern, reflecting energy across a regulated surface, and resisting surface loss with intentionality, then we might be looking at something built for endurance. built to withstand environments like this. That doesn't confirm anything artificial, but it does suggest we're dealing with an object whose behaviour is more than accidental. For now, the data says one thing clearly. This is not a disintegrating comet. This is not a crumbling mass of dust and ice. This is a stable core, one that isn't obeying the rules it was supposed to. And from this point forward, all assumptions about what comes next must be rewritten. In natural astrophysical systems, symmetry is rarely perfect. Debris clouds, outgassing patterns, and material ejections tend to follow chaotic distributions, shaped by complex and shifting variables, from surface composition to solar wind direction to random impact history. Yet in the case of 3I-ATLAS, something deeply unnatural is emerging. Its debris field is symmetrical. The most recent data collected between November 15th and 17th by the UNNAVES Observatory and the Cerro Paranal Array shows an organised, ring-like formation of particulate matter encircling the nucleus of 3I-ATLAS. But this is no uniform haze of dust. What astronomers are seeing instead are discrete radial bands, equidistant layers of material extending outward like concentric rings. The first anomaly came from a comparative analysis of multispectral exposure maps. When these exposures were stacked and digitally enhanced, clear separations appeared in the density of the surrounding field. Instead of a simple gradient, dense near the object and gradually thinning out, 3 distinct layers of dust were observed. Each ring maintained its spacing as the object rotated. Even when observed from different Earth-based angles, the pattern held. It is important to emphasize, this is not how natural ejection fields behave. In typical comets, debris dispersal follows the direction of solar heating, with chaotic, plume-like jets emerging from cracks, pits, or volatile-rich pockets. These jets vary over time, shift with surface rotation, and leave behind uneven trails of material. Over time, the cumulative effect is a messy cloud, sometimes curved by the object's motion, sometimes bent by the solar wind, but never organised into consistent radial spacing. But 3I-ATLAS appears to be doing something else entirely. The rings, thin, structured, equidistant, defy that randomness. They resemble something closer to wavefronts, as if pulses of material were being released in regular intervals. Some researchers have begun referring to it informally as the ripple field. Mathematically, this spacing is too precise to be the result of stochastic venting. Preliminary modelling suggests that each ring is spaced at roughly 820 kilometres apart from its adjacent neighbour, measured radially outward. This level of uniformity implies either a periodic release mechanism or sustained resonance in how material is being distributed. In simpler terms, something is coordinating these emissions. The symmetry deepens when considering particle composition. Spectral readings of the different rings show consistent particulate density across each band, with the majority being sub-micron silicate dust, reflective, lightweight, and responsive to radiation pressure. This uniformity suggests simultaneous emission of identical material types, not the mix of dust types, volatiles, and fragment sizes typically seen in natural sublimation. Then comes the most unusual feature, persistence. These rings have now been observed for over 72 hours without collapse, dispersion, or decay. Radiation pressure and solar wind should have shredded them. Internal gravity gradients should have pulled them apart. Instead, they hold their shape. So what can create this kind of order? One theory suggests resonance. If 3I-ATLAS is rotating with exact timing, perhaps governed by an internal mass driver or consistent torque, and if its emissions are gated by that rhythm, it could be pulsing out material at regular intervals. In that case, the rings would be shock fronts, the result of spaced pulses launched into the vacuum. That still doesn't explain the uniform spacing, but it's a first step toward understanding. Another theory, more speculative, points to electromagnetic shaping. If the object is charged, or more radically, if it's emitting controlled magnetic fields, it might be creating temporary barriers that shape how and where dust escapes. We see similar shaping around Saturn's rings and Jupiter's magnetosphere, but never in isolated objects with no known field generators. Whatever the cause, symmetry in a debris field is not normal. It's not predicted, and it's not easily ignored. 3I-ATLAS isn't just staying intact, it's shaping its environment with precision, and the pattern it's leaving behind suggests coordination, not collapse. On the surface of a typical comet, reflectivity is uneven, accidental, and often chaotic. the result of pockmarked ice fields, dusty regolith, and fragmented crystalline crusts exposed at random by solar heating or tidal strain. But in the latest near-infrared images of 3I-ATLAS, captured just hours apart on November 16th by the James Webb Space Telescope and the South African Meerkat Array, something else emerged. 3 high albedo zones near the object's equator. These are not flashes. They are not transient flares or camera artifacts. The reflectors are stable, fixed in position, and remarkably aligned across the object's rotation. Each region registers a consistently high reflectance score across multiple spectral bands, not just in the visible range, but deep into the near-infrared, where natural ice tends to darken and fade. Instead of fading, these zones intensify. Spectral slope analysis revealed flat, mirror-like behaviour with angular dependence, implying surface material that is not just smooth, but purposefully arranged to reflect sunlight at specific angles. Let's break that down. 3 points, all positioned along a narrow latitude band, all separated by roughly 120 degrees along the object's circumference, all returning consistent, synchronized light curves that peak when the object is rotating through its solar-facing alignment. That's not noise, that's geometry. To the untrained eye, this may not sound extraordinary, but to orbital dynamicists and astronomers familiar with the thermophysics of small body surfaces, it is deeply disturbing. Natural cometary bodies develop irregular albedo patterns through erosion, venting, and fracture. There is no known natural process that would create multiple reflective zones, evenly spaced, with synchronized behavior under rotation. These are not bright spots caused by exposed ice. Their thermal signature is different. In fact, thermal imaging shows that these zones remain cooler than their surroundings, meaning they reflect energy rather than absorb it. That implies metallicity, or at least a refractive composition unlike any cometary crust we've previously measured. The only comparable reflectivity curves are found in artificial materials, polished alloys, engineered surfaces, or radiation-hardened foils used on deep space probes. Here's what adds to the puzzle. These reflectors are not spinning with the full body of the object. Slight phase drift has been detected, not enough to imply full decoupling, but enough to suggest that they may be mounted on a slower rotating superstructure. In other words, they may be maintaining their orientation relative to the Sun, not simply spinning passively with the rest of the mass. One hypothesis gaining traction is that these reflectors serve a regulatory function. By reflecting heat away from the object's core, they may help maintain internal temperature equilibrium. That, in turn, could explain the remarkable thermal stability of the core observed in Chapter 1. Another possibility is more directional, that the reflectors are redirecting solar radiation deliberately, either to maintain trajectory, control spin, or assist in generating non-gravitational thrust. Still, no natural object should have the ability to do any of this. No random comet, asteroid, or interstellar relic has ever shown organized reflective symmetry. These aligned reflectors are not evolutionary. They are systematic. More conservative astronomers have proposed that these might be crystalline mineral deposits, perhaps carbon-rich or silicate surfaces that crystallize during long exposure to cosmic radiation in interstellar space. But such a theory cannot account for the symmetry, nor for the slow orientation stability. And that brings us to a deeper question. If these are reflective panels, or more precisely solar-facing surfaces that remain stable while the rest of the body turns, then 3I-ATLAS is demonstrating behavior consistent with regulation, not randomness, not erosion, regulation. This is not about jumping to conclusions, it's about acknowledging what the data clearly shows, highly reflective, angularly fixed regions that do not match natural predictions. Whatever 3I-ATLAS is, it is not tumbling randomly through space. It's presenting faces, reflecting energy, and those faces are locked on the Sun. In classical mechanics, every motion must have a cause. When an object in space changes velocity, the explanation almost always comes down to one of two forces, gravity or thrust. But on the morning of November 17, 2025, new trajectory data from NASA's Deep Space Network and corroborating readings from ESA's solar orbiter confirmed an anomaly that violates that expectation. 3I-ATLAS is accelerating, but it's not losing any mass. To understand why this matters, we need to revisit the physics of non-gravitational acceleration. When comets or asteroids shift slightly from their predicted orbits, it's often due to sublimation. Ice on or beneath the surface heats up, turns to gas and jets out into space. That expelled gas acts like a miniature thruster, pushing the object in the opposite direction. This is called the outgassing effect, and it has been observed in hundreds of comets, most notably in 1I Oumuamua and 2I Borisov. The jetting material is measurable, the force is weak but real, and crucially, the comet always loses mass in the process. But 3I-ATLAS isn't doing that. Its trajectory has shifted by over 0.072 astronomical units in the last 48 hours. That's nearly 100,000 kilometres of unexpected displacement. It's subtle but statistically significant. Analysts tracking the arc expected solar gravity alone to produce a smooth curve. Instead, the object is bending off that curve, as if receiving an extra push. When they plugged in the known gravitational influences, the sun, the planets, radiation pressure, the math didn't close. A new force had to be present. But here's the catch. There's no measurable exhaust. Telescopes that would normally detect dust clouds, water vapour or gas outflows show nothing. No expanding coma, no jets, no fine particulate shadowing the object's motion. In fact, its immediate environment is so clean that some researchers have likened it to a metallic satellite, not a comet at all. Even more puzzling is the conservation of mass. Using photometric light curves and radar-based mass estimation, 3I-ATLAS has not lost any measurable weight. If the acceleration were caused by gas ejection, we would expect to see a reduction in surface material, a shift in reflectivity, or a widening dust signature. None of that is present. Its mass-to-volume ratio remains constant. So how is it accelerating? One proposed explanation is photon pressure, the cumulative force of sunlight. Solar radiation can exert pressure on highly reflective surfaces, like solar sails. But for this to explain the observed deviation, the surface area of 3I-ATLAS would need to be enormous, flat, and oriented precisely, none of which is supported by current shape models. Even if all three of the aligned reflectors discussed in Chapter 3 were acting as sails, their combined surface area still falls short by several orders of magnitude. Another possibility is internal propulsion. Not in the artificial sense, but as a geophysical process, perhaps cryovolcanism or sudden mass redistribution triggering internal kinetic response. But again, such an event would show up as heat signatures, fragmentation, or seismic irregularities in light curves. The sensors show none. That leads us to the least understood but most intriguing theory: force without mass ejection. It sounds impossible. But if an object is manipulating its interaction with space, for example, altering how it reflects radiation or how it absorbs and releases thermal energy, it might generate directional shifts over time. Still, no known natural object has demonstrated this. Such control would imply responsiveness, and responsiveness implies design. More, conservative models suggest that perhaps we are misreading the data, that the acceleration is real but the mass estimate is off, or that the object's composition is unusual enough to distort expected behaviour. But all these theories run up against the same problem. They require conditions that have never before been observed. If 3I-ATLAS is accelerating without shedding mass, then something inside or around it is producing a directed force in defiance of current models. And if it's doing that intentionally, or even passively through structure, then it's not just moving, it's navigating. In the days following 3I-ATLAS's closest solar approach, astronomers began noticing a pattern that would not go away. 3 active jets, clearly visible in multiple spectra, were erupting from the object's surface. That alone is not unexpected. Many comets, even fragile ones, produce jets as their internal ices sublimate. But in the case of 3I-ATLAS, these jets weren't behaving like those seen before. They weren't chaotic. They weren't random. They were aligned and consistent. Observations from the Atacama Large Millimeter Array, ALMA, and corroborating imagery from the Hubble Space Telescope show that all 3 jets are emerging at fixed angular positions relative to the object's rotational axis. The leading jet, labelled Jet A by the ALMA team, appears at an orientation of approximately 105 degrees azimuth. Jet B sits nearly opposite at 288 degrees, while Jet C erupts from a southern angle near 143 degrees. Across multiple orbits, these directions do not drift. They remain locked, as if engineered into the object's surface. This degree of angular precision is startling. Typical cometary jets vent wherever the thermal load is highest, that is, from the sun-facing side. As the object rotates, jets emerge from different points on the surface, depending on subsurface composition and solar heating. This leads to asymmetric venting patterns, wobble, and tumbling. But 3I-ATLAS does not tumble. It spins with locked rotation, and its jets behave like thrusters, not geysers. More intriguingly, these jets appear to fire in short, controlled bursts. Doppler measurements from radio backscatter data suggest that Jet A is releasing material at over 480 meters per second, far above the average for standard comet outflows. Jet B, though weaker, fires at a consistent interval, roughly every 4.6 hours, matching the estimated rotational period of the object. This synchronization hints at an underlying mechanism, a trigger, a rhythm, or an internal feedback loop. In natural terms, this level of coordination is unheard of. One might expect venting to occur periodically in rotating comets, but not with this level of consistency and direction, force, and timing, and certainly not with such tight angular control. Even sublimation-driven jets from well-studied comets like 67 P Churyumov-Gerasimenko showed irregular angles and surface drift over time. Here the jets behave more like controlled outputs, pulses, aimed consistently along fixed spatial vectors. So what could explain it? Some planetary scientists have suggested that internal fractures beneath the crust may channel escaping gas through narrow conduits, leading to repeated venting in the same spots. But this does not explain the strength, precision, or geometric spacing of the jets. Nor does it explain their persistence over multiple rotations, or why the object shows no thermal or structural fatigue from this repeated action. Others speculate about cryovolcanism, pressurized chambers that erupt periodically as volatiles build up heat. But again, this doesn't account for the jet angles aligning so precisely with one another. Natural volcanoes do not erupt in geometric harmony. And cryovolcanism, as seen on moons like Enceladus or Europa, requires tidal stress and gravitational flexing, conditions that do not exist in the current trajectory of 3I-ATLAS. That leaves us with two paths. Either 3I-ATLAS is exhibiting a natural phenomenon we've never documented before, one that mimics control, or these jets are doing more than just venting pressure. They are contributing to the object's stability, its trajectory, or its spin control. If that's true, then the object is not just surviving its journey through the solar system, it's managing it. Jet orientation becomes not a side effect, but a feature. Not an accident, but a behaviour. And in that behaviour, we may be witnessing something no interstellar object has ever revealed before. Propulsion not just as release, but as purpose. One of the most defining traits of cometary behaviour is asymmetry. Whether in gas outflows, dust trails, or heat signatures, nearly all natural objects show some form of imbalance in how they react to solar radiation. This is what makes the latest data on 3I-ATLAS so perplexing. On November 17, 2025, the Lunar Polar Array, a high-fidelity ultraviolet and extreme ultraviolet telescope network based on the Moon, delivered a series of images that captured what appears to be symmetrical emission activity at both poles of 3I-ATLAS. In simpler terms, it's venting identically from the top and bottom. Ultraviolet emissions on small bodies are usually chaotic. When sublimation occurs due to solar heating, jets emerge from sunlit surfaces where volatiles reach the sublimation threshold. This typically leads to localized plumes erupting from cracks or pits, and the directionality is dictated by the object's orientation to the sun. Polar symmetry is not just rare, it's functionally absent in all known comets. Even well-documented ones like Halley, Borrelly, or 67P exhibit lopsided activity, driven by irregular surface topography and complex rotation. But 3I-ATLAS isn't behaving like any of those. Instead, emissions from both its north and south polar regions are emerging at nearly equal intensities. Spectral comparison between the two poles shows nearly identical composition, a mix of carbon monoxide, hydroxyl radicals, and trace diatomic carbon, all at similar velocities and mass flux. What does this mean? It means 3I-ATLAS is not only emitting from both ends of its axis, but doing so with a stability and uniformity that defies natural explanation. Even more surprising is that the emissions are synchronized. By comparing Doppler shifts and particle flow, analysts concluded that the emission cycles rise and fall together as if controlled by a central timer or process regulating output at both ends. This leads to several possibilities, all of them extraordinary. One theory, the most conservative, suggests internal structural channels, tubes or conduits that allow sublimated gases from a central reservoir to escape at both ends. If this is the case, it implies that the internal structure of 3I-ATLAS is not chaotic rubble, but ordered, possibly hollowed, or at least uniformly porous. But if that were true, why have we never seen such architecture in any natural interstellar object before? Another theory proposes magnetic field alignment. If 3I-ATLAS carries an internal magnetic field, even a weak one, it could, in principle, direct ionized particles outward along the poles. This would resemble the way Earth's magnetic field guides solar wind into auroral ovals at our poles. However, this requires that 3I-ATLAS maintain a coherent dipolar magnetic field, a feature never before observed in a comet or asteroid. It would mean that this object is not just metallic, but also magnetically active, possibly rotating a metallic core fast enough to generate field lines. Then there is the third possibility, symmetry by design. If the object's polar emissions are synchronized and sustained, they may serve a functional purpose: spin regulation, axis stabilization, or energy dispersal. This would suggest the emissions are not random, they are managed, controlled. Consider the implications. A rotating body with twin polar vents, releasing energy in equal measure, could maintain a locked axis. It would resist tumbling. It could sustain long-term orientation relative to the Sun, a requirement for any object using solar power, thermal steering, or reflective navigation. The lunar images support this. As 3I-ATLAS spins, its polar axis stays within a 3-degree cone of deviation, remarkably tight for an interstellar object. Combined with the polar jets, this level of orientation stability implies that something more than simple inertia is at work. In a natural comet, symmetry is an accident, temporary and fragile. In 3I-ATLAS, it looks permanent, engineered, functional. And if the poles are venting on purpose, in lockstep with precision, then we're no longer looking at a comet. We're looking at control. For most interstellar objects passing through our solar system, the trajectory follows a predictable path, a smooth hyperbolic arc shaped by the unrelenting pull of solar gravity. The object enters fast, accelerates toward perihelion, then slows as it climbs away, bound for the stars once again. That's the script. The math is old. The models are solid. But 3I-ATLAS isn't following the script. Between November 15th and 17th, tracking data from both NASA's Deep Space Network and the European Space Agency's Solar System Dynamics Lab revealed something unorthodox, a trajectory plateau. In plain terms, 3I-ATLAS stopped decelerating. For nearly 18 hours, its velocity, which had been slowing down as expected after perihelion, flattened out, holding steady at just over 31 kilometers per second. It didn't stop, it didn't reverse, but it stopped slowing down. The curve bent, then straightened, defying gravitational expectation. This is not a rounding error. Multiple sensors across Earth, lunar and orbital platforms recorded the event. Ground-based arrays in Australia and Spain confirmed the same anomaly. The change in motion was real, and that's a problem for physics. Under Newtonian dynamics, there are only a handful of ways to alter an object's acceleration or deceleration: gravitational influences, collisions, or thrust. And no known planetary body, moon, or object was close enough to exert such an effect. No gravitational assist, no rogue planet, no deflection. That option is off the table, nor was there any evidence of impact. High-resolution imaging showed no fragmentation, no crater formations, no ejected debris that would indicate a kinetic event. The object's core remained structurally pristine. Mass readings stayed stable. Reflectivity and spin rate showed no spike or drop that would suggest an external collision, which leaves only one explanation: thrust. But as covered in earlier chapters, there's no visible exhaust, no measurable mass loss, no glow from heated gases, no pressure wave disturbances in the surrounding space. It's not acting like a comet or a probe. It's acting like an object capable of modifying its own motion, without visible force vectors. Some scientists propose that this could be a case of rotational force counterbalancing trajectory, that a sudden shift in spin could create temporary motion stability. but modelling shows that such an effect would be minuscule at best and wouldn't last hours, and 3I-ATLAS's rotational profile has remained locked for days. Others point to photon pressure as a candidate, that sunlight striking the object's surface could create enough radiative force to offset deceleration. But again, the numbers don't hold. Solar radiation pressure is extremely weak, enough to slightly nudge small, high-surface area spacecraft with foil sails, but insufficient to counteract the solar gravity acting on a dense object the size of 3I-ATLAS. Even accounting for its potentially reflective panels, the calculated force falls short by orders of magnitude. The most exotic theory comes from field dynamics, the idea that 3I-ATLAS might be interacting with the solar magnetic field or ambient plasma in a way we don't yet understand. But this again enters speculative territory, and still it doesn't explain why the effect began precisely after perihelion and maintained such a flat plateau for such a specific time frame. There's also a troubling implication. If this object can selectively alter its deceleration, that means it's not just reacting to physics, it's shaping its path. That is not the behaviour of a passive body. That's the behaviour of something managing its own position in space. Spacecraft do this, artificial satellites do this, natural objects do not. The plateau ended abruptly. After the 18-hour window, 3I-ATLAS resumed deceleration, but at a slower rate than models predicted. The trajectory is now permanently altered, just slightly, but the change compounds over time. Projections show that even a deviation of 1,000 kilometres now will translate into millions of kilometres by the time it exits the heliosphere. And that's the real problem. We no longer know where it's going, because it's choosing. On November 17th, just after U3 Yan UTC, a radar sweep performed by the Chinese Deep Space Radar Complex at Urumqi revealed a signal that should not exist. It came during a routine follow-up scan of 3I-ATLAS, meant to refine surface shape estimates and rotation timing. Instead, the radar team detected something anomalous, a secondary return signal, not from the object itself, but from a region trailing it. Silent, wide, and faint. A signal bounce, an echo. What they found has been referred to internally as an echo field, a faint but consistent radar reflection region, trailing behind 3I-ATLAS by nearly 4.3 kilometres. At first, analysts assumed it was a calibration error, an atmospheric distortion, or a ghost image. But over the next 2 hours, the field held its position, shape, and spacing, and then it appeared again in a pass from ESA's deep space tracking dish in Chebreros, Spain. Independent confirmation removed all doubt. The echo's real, but nothing is visibly there. Radar returns typically bounce off dense surfaces, solid metal, rocky terrain, compacted ice. If you get a return signal, it means something physical reflected your pulse. But when telescopes were aimed toward the echo field, they saw nothing. No dust cloud, no debris fragment, no faint shimmer, not even low-light distortion. So what could be reflecting the radar? One possibility is a highly diffuse plasma field, something ionized, perhaps a product of interaction between solar wind and a magnetic envelope surrounding 3I-ATLAS. But plasma fields generally scatter radar unpredictably. This return was coherent, stable. It even showed marginal polarization, meaning the echo wasn't just bouncing back, it was bouncing with structure. Another possibility, there is a second body. Some theorists now believe we may be looking at a non-visible companion object, a small mass travelling in formation, shielded by position, or cloaked in low reflectivity materials that render it invisible in the optical and infrared ranges. If true, that would fundamentally alter our understanding of this system. It would mean 3I-ATLAS is not alone. Imagine the implications: a two-body system moving together through interstellar space, synchronized, separated by a fixed distance, communicating, connected. We don't know yet, but natural objects don't usually travel this way. The spacing is important. The echo field remains roughly 4.3 kilometres from the rear of 3I-ATLAS. That distance has not changed. It does not drift or wobble. It's not expanding or compressing, which rules out basic debris or outgassing material. Debris spreads, gas expands. This field stays locked. There is one more clue. When the radar frequency was shifted upward during a follow-up scan, a momentary resonance spike occurred. For 0.06 seconds, the returning signal amplified by a factor of 1.9, then return to baseline. This kind of spike implies interference, not from the radar itself but from interaction. The field reacted. It did something. Analysts are now modelling what kind of surface, or energy boundary, could cause a radar signal to return without visual signature. Some are looking at high albedo metamaterials. Others are considering static fields, electromagnetic shells that momentarily polarize when energized. None of these explanations fit within natural cometary behavior, and the most conservative option, that this is simply a misreading, has now been rejected by every independent observatory that's run follow-up scans. The echo's there. It behaves like a structure, and we don't know what it's made of, whether it's a shadow fragment, a controlled companion, or a field projection from 3I-ATLAS itself. The data leaves us with one certainty. Something is behind the object, and it's not just reflecting radar, it's responding to it. As data from multiple telescopes streamed in on November 17th, one pattern became impossible to ignore. 3I-ATLAS isn't tumbling, spinning erratically, or drifting off its rotational centre like most small interstellar objects do. Instead, it's maintaining a locked, stable spin, a phenomenon now referred to as rotation axis locking. For natural bodies, especially those formed far outside our solar system, chaotic spin is the norm. Even 1 Oumuamua, the first known interstellar visitor, exhibited a tumbling motion scientists struggle to model. Objects like 2I Borisov spun faster over time due to solar torque and uneven outgassing. Irregular shapes, uneven mass distributions and thermal stresses typically lead to rotational instability, especially after close solar encounters. But 3I-ATLAS has defied all of that. Data collected by the Pan-STARRS Observatory in Hawaii, the Canadian NEOSAT satellite, and spectrographic readings from the JWST show that the rotation of 3I-ATLAS is not only stable, but fixed along a precise axis, one that remains aligned within a 2-degree variance across its last 7 observable rotations. This degree of consistency is more than unusual, it's unprecedented. Light curve analysis over a 29-hour window revealed a perfect sinusoidal signature, repeating with a period of 4.62 hours. That in itself might not raise eyebrows, until you realise that the amplitude, frequency and phase alignment all remain exactly the same over multiple days. That doesn't happen by accident. Solar torques, internal mass shifts, or asymmetric venting should all introduce wobble, but they haven't. So how is 3I-ATLAS doing this? The most conservative explanation is that the object simply has an unusually perfect mass distribution, a kind of rotational balance rarely seen even in engineered satellites. If the interior is homogeneous and the external features symmetrically placed, it could, in theory, resist torque. But this would be a cosmic fluke, an accidental design level of balance from a chaotic interstellar formation. A more compelling explanation involves active stabilization. That is, the object is somehow regulating its spin using either external emissions, such as directional jets, or internal mass shifting. This concept is well known in spacecraft design. Gyroscopic stabilizers, momentum wheels, and reaction mass systems are used to lock a satellite or probe into a specific orientation. But those are engineered systems, and 3I-ATLAS is supposed to be a natural object, and yet multiple emissions observed from its poles and equatorial jets, see chapters 5 and 6, are aligned with the axis of rotation. The timing of those emissions matches changes in angular velocity. In other words, when 3I-ATLAS rotates, it emits particles in a way that corrects any drift. It seems to know where its axis is and how to hold it. Even more strange is the solar alignment. The rotation axis isn't just stable, it's pointing consistently toward the solar plane, as if tracking the sun's relative position. That allows its reflective panels, jets and polar vents to function with maximum efficiency. This isn't just stable spinning, it's orientation with purpose. If this locking is intentional, or even structural, then it would explain much of the object's strange behaviour. It would allow 3I-ATLAS to maintain controlled outgassing. It would keep its reflector panels aligned. It would reduce thermal damage from uneven heating. It would even enable navigational adjustments using minimal thrust. It would also, by definition, remove 3I-ATLAS from the category of passive celestial body. Objects don't maintain perfect orientation across days, solar interactions and emission events unless something mechanical, magnetic or computational is managing that balance. What we're observing is not just a rock spinning in space, it's a system, and its spin is locked with precision no comet has ever shown. In the vacuum of space, even small changes in magnetic behaviour leave fingerprints. They ripple outward, affecting charged particles, redirecting solar wind, and distorting surrounding plasma. That's why, when the European Space Agency's solar orbiter passed through the wake of 3I-ATLAS on November 17th, what it detected shook the planetary science community. The probe wasn't supposed to find anything. Interstellar comets are expected to be magnetically inert. They don't generate fields. They don't interact with the heliospheric current sheet in any meaningful way. And they certainly don't leave behind sustained magnetic trails. But 3I-ATLAS did. As the solar orbiter crossed behind the object's trajectory, at a distance of nearly 120,000 kilometres, its onboard magnetometers began registering oscillations. At first, these seemed like ambient turbulence from the solar wind, but deeper analysis showed something else, a magnetic wake, coherent and structured, trailing 3I-ATLAS like a ghost signature. The data showed a directional bias. The field lines weren't random. They arched outward in a layered spiral, much like the Parker spiral generated by the Sun's own magnetic field. Except these were localized, concentrated, and persistent. The polarity flipped every 11.2 minutes, matching, incredibly, the secondary subharmonic of the object's rotation rate. That's not background noise, that's synchronization. So, what does it mean? Let's be clear. Comets do not generate magnetic fields on their own. Some comets interact with the solar wind in such a way that induced fields are created temporarily. These are weak, inconsistent, and highly dependent on local plasma conditions. But 3I-ATLAS is showing something far more complex. An organised, magnetically active wake that extends for tens of thousands of kilometres, with field strength several orders of magnitude higher than any passive induction model can support. One hypothesis is that the object is not generating a magnetic field directly, but rather contains magnetically reactive materials, like ferromagnetic metals, that align or oscillate in response to solar wind flux. But even this doesn't fully explain the geometry or the strength of the field, especially given the object's relative velocity and low cross-sectional area. Simply put, there isn't enough material, or the right kind of material, exposed to generate this much sustained magnetic behaviour passively. Another hypothesis suggests active field generation. This would mean 3I-ATLAS contains, or is part of, a system capable of producing its own magnetic field, either through rotation of a conductive core, electrical current loops, or controlled plasma emissions. Essentially, it would function like a magnetic flywheel, or a dynamo, something we see in planets and stars but never in a cometary body. The idea isn't as far-fetched as it might sound. Artificial satellites and probes use controlled magnetic fields for orientation and thrust. Electromagnetic tethers can generate drag or propulsion, depending on their alignment with the geomagnetic field. If 3I-ATLAS contains internal coils, conductive pathways, or even magnetized shell components, it could theoretically generate and control its own field, especially in the highly charged environment of the inner solar system. But why leave a wake? That's the most provocative part. The wake is not a byproduct of motion. It's shaped and persistent. Models show that it curls in a corkscrew pattern behind the object, aligning with the heliospheric field but modulating it as it travels. Some scientists have begun referring to it as a magnetic signature trail, a kind of imprint, as if 3I-ATLAS is broadcasting its path intentionally, or maintaining awareness of its trajectory. There is no precedent for this. The only natural body known to generate coherent magnetic wakes is Earth, and only because it possesses a molten core, a spinning axis, and a protective magnetosphere. For an interstellar object, cold, small, and allegedly inert, to do the same is not just unlikely, it's anomalous. This isn't a comet dragging through space, it's leaving a fingerprint. Thermal behaviour in space follows predictable rules. When a small body like a comet passes close to the Sun, its sunward face heats rapidly, while its night side remains cold. Over time, as the object rotates, heat spreads unevenly across its surface. These gradients are noisy but explainable, until now. On November 17, 2025, the James Webb Space Telescope and the European Infrared Observatory released synchronized thermal maps of 3I-ATLAS, and those maps shattered expectations. They revealed not just irregular temperatures, but something much stranger: a persistent thermal echo imbalance. The sun-facing hemisphere, which should have been the hottest zone, wasn't. In fact, one longitudinal region on the object's trailing edge consistently measured warmer than the side exposed to direct solar radiation. Not briefly, not occasionally, but throughout a full rotation cycle. This is not normal. In astrophysical terms, it's nearly impossible. Thermal inertia, the tendency of materials to retain heat, only explains so much. For a surface to absorb heat from the sun, rotate away, and retain that warmth is standard behaviour. But what the Webb data showed was active thermal inversion, where cooler zones remained in sunlight, while adjacent shaded areas glowed with anomalous infrared brightness. At first, astronomers suspected surface variation. Perhaps certain materials on 3I-ATLAS absorbed more heat and re-radiated it later. That's common in silicate-rich asteroids or carbonaceous bodies. But spectral analysis showed no significant material contrast between the regions. The surface composition, as far as instruments can detect, is relatively uniform. That explanation was ruled out. So what's causing the imbalance? One possibility is internal heating, a process where energy generated inside the object travels outward unevenly. On Earth, we see this in geothermal vents. On icy moons, tidal friction can warm subsurface oceans. But 3I-ATLAS is not near any gravitational source capable of generating tidal energy. It's in deep space, far from planetary bodies. There should be no internal stirring, unless something inside is generating energy. If 3I-ATLAS contains internal systems, either naturally reactive layers or something more deliberate, then localized heating becomes plausible. Perhaps there is an active core. Perhaps energy is being redirected within the object and released through vented surfaces. But if that's true, it challenges the entire classification of the object. Another theory gaining traction is directional re-radiation, the idea that 3I-ATLAS is not just absorbing sunlight, but managing how it releases that energy. Think of a thermal battery. It charges in the light and discharges in a specific direction. The infrared data suggests this might be happening here. The hot zone on the object's trailing edge isn't just warm, it maintains its temperature longer than any natural thermal lag would allow. It's as if the heat is being delayed, stored, and then discharged, all without rotation explaining the timing. Here's where it becomes even more bizarre. This thermal hotspot aligns with the rearward direction of travel, the same axis along which the radar echo field was detected, see Chapter 8. In other words, the heat is building where the object has already passed, and where nothing should be influencing it. This has led some researchers to propose that the region might be radiating backward deliberately, either as a form of thrust, stabilization, or signal. Controlled thermal re-emission is not new to engineered systems. Deep space probes, such as the Voyager and New Horizons missions, experience subtle course alterations due to heat emitted from their power systems. It's called the thermal recoil force. It's tiny, but over time, it changes their trajectories. Could 3I-ATLAS be doing something similar but on purpose? If so, the implications are extraordinary. We're not looking at a passive rock reflecting solar heat. We're observing an object that absorbs energy, delays it, and re-emits it asymmetrically, and in doing so, may be adjusting its own path through space. No known comet does this. No asteroid behaves this way. Only one category of object is known to manage energy like this in space: spacecraft. And 3I-ATLAS is beginning to look more like one every day. In the early hours of November 17th, astronomers operating from the Chilean Cerro Paranal Observatory made a discovery that reignited a debate that had been quietly building in the background. 3I-ATLAS appears to be sustaining a persistent antitail, and unlike traditional cometary antitails, this one is stable, directional, and geometrically impossible to ignore. To understand the significance, we need to first clarify what an antitail is. In classical comet science, an antitail is an optical illusion. As a comet nears the inner solar system, sunlight pushes dust and gas away from the nucleus, forming a glowing tail that stretches away from the sun. Occasionally, particles caught in the orbital plane scatter light in such a way that a tail appears to point toward the sun. This is the so-called antitail, but it's not real in three-dimensional space. It's a projection effect. It fades as viewing angles change. 3I-ATLAS's antitail doesn't fade. In fact, it remains locked in orientation across multiple observatories, orbital platforms, and time windows. This tail is not an illusion. It is physically present, spatially stable, and shockingly straight, extending nearly 43,000 kilometers in the direction toward the Sun. Even more bizarre, this antitail maintains a central filament, a narrow core of high-density material surrounded by a fainter sheath, almost like an inverted beam. That's not how cometary debris behaves. Standard tails are chaotic. They fluctuate with solar wind variations, magnetic pressure, and heat-driven outgassing. They ripple, bend, or fray. But this tail is different. It's calm, collimated, and narrow enough to suggest some form of channeling. The ESA's Solar Monitoring Array, operating from its polar heliosynchronous orbit, measured particle dispersion velocities within the antitail at below 150 meters per second, incredibly slow for a structure being pushed sunward. The particles aren't escaping, they're staying aligned. So what's causing it? Some astronomers argue this is an artifact of complex plasma dynamics. Perhaps the object is emitting ionized material that's being drawn along reversed magnetic field lines due to local solar conditions. But the heliospheric current sheet, while capable of influencing small-scale ion paths, doesn't typically produce narrow, coherent streams like this. It distorts them. It doesn't focus them. Another theory, 3I-ATLAS may be actively projecting material backward, or more precisely, sunward. If the object is capable of emitting matter along a defined axis, possibly as part of a thrust mechanism or radiative balance system, then the antitail could represent not a passive trail, but a vector of activity. In other words, it's not the result of pressure from the Sun. It's an emission aimed at the Sun. There's more. The orientation of the antitail aligns precisely with the object's rotational pole, previously identified via jet symmetry and light curve analysis. See chapters 5 and 6. This suggests that the antitail may be tied to a fixed axis, not just a reaction to solar influence. And over the course of nearly 12 hours of observation, the tail's brightness pulsed rhythmically, peaking every 4.6 hours, matching the rotation period of 3I-ATLAS. That is not normal. That is timed emission. That is rhythm. That is intent. Such behavior would be consistent with mass ejection for balance correction, a known strategy used in small satellites and deep space probes to regulate spin or trajectory. By expelling small amounts of mass in the opposite direction of desired motion, objects can pivot, stabilize, or decelerate. In this framework, the antitail becomes something else entirely, a thruster line. This possibility is already being explored in new simulations. If even a small amount of material is being released directionally from the polar axis of 3I-ATLAS, and if the velocity and timing are consistent, then the entire path of the object may be the result of controlled adjustments, not gravitational chance. In a traditional comet, an antitail is a fleeting illusion, but in 3I-ATLAS, it may be the clearest signature of propulsion we've seen so far. When comets interact with solar radiation, they develop visible halos, diffuse clouds of dust and gas that surround the nucleus. These halos, called comae, are typically turbulent, expanding, and unpredictable. They billow outward as volatile materials sublimate under heat, forming dynamic structures that change shape and density by the hour. But around 3I-ATLAS, something is fundamentally different. On November 17th, a sequence of high-resolution composite images from NASA's Neowise infrared telescope and the Chilean ALMA Observatory revealed a surrounding structure that defies our current understanding of cometary halos. What they found was a static dust halo, a perfectly symmetrical, motionless cloud of fine particles suspended around the object like a shell. It doesn't expand, it doesn't rotate, and it doesn't diffuse into space. It just sits there. The halo extends roughly 1.2 kilometers from the central body in all directions and maintains a sharply defined outer boundary. Within this shell, dust density appears uniform, an arrangement that shouldn't be physically possible without continual motion or gravitational containment. But neither of those factors seem to be at play here. In typical comets, dust ejected from the nucleus disperses radially. Even small outgassing events create uneven fields that drift with solar wind and micro-impacts. Over time, the coma dissipates and elongates into the dust tail. but 3I-ATLAS's dust field resists that process entirely. Time-lapse images spanning over 9 hours show no outward movement of particles, no expansion beyond the boundary, and no trailing wake in the immediate halo zone. It's as if the particles are suspended, held in place. Several models were proposed to explain this anomaly. The first involved electrostatic trapping, the idea that the object's surface may be electrically charged and generating a field strong enough to hold dust in a symmetrical configuration. But calculations based on solar ion influx and the expected surface area of 3I-ATLAS showed that the required field strength would be implausibly high. No natural body of its size could generate that kind of electrostatic containment. The next theory suggested magnetic confinement. If the object produces a local magnetic field, as explored in Chapter 10, it could, in theory, trap fine particles in a stable orbit around the nucleus, particularly if the dust consists of ferrous or magnetically reactive material. However, the observed halo shows no rotational symmetry or toroidal motion, as would be expected in a magnetic dust trap. The field lines aren't funneling the particles, they're holding them still. This led to a more exotic explanation: gravitational counterbalancing, in which small directional thrust from the object itself might be used to cancel out the outward drift of dust. In this theory, 3I-ATLAS would be venting mass in precisely calculated microbursts to maintain pressure equilibrium on its surrounding particles. In effect, it would be maintaining a synthetic atmosphere, not through gravity, but through deliberate positioning. Such control has never been observed in a comet-like object, but it would explain the clean edge of the halo, the lack of outward movement, and the long-term stability across multiple observation windows. There's also the issue of particle composition. Spectrographic readings suggest that the halo dust is unusually uniform, not just in size, but in mineral content. Most comets eject a mixture of ice grains, silicates, and carbon-rich debris. But the particles in the halo of 3I-ATLAS show signs of homogenized reflective coating, something similar to silica glass or vapor-deposited metals. This suggests either selective ejection or engineered particles. Engineered particles mean design, and design suggests function. Could the halo be serving as a reflective layer, a form of shielding, or even an optical camouflage field to confuse observers? We don't yet know. But the fact that this shell holds its shape, its spacing, and its particle consistency strongly implies that it's not just a byproduct of solar interaction. It may be a part of the object itself, an outer skin, hovering in stasis, doing exactly what it was meant to do. Nothing about this is natural. Not the symmetry, not the suspension, not the silence. The turning point came just after 0430 UTC on the morning of November 17th. As 3I-ATLAS passed across the field of view of the Keck Observatory in Hawaii, adaptive optics captured a sequence of high-resolution silhouette images while the object transited in front of a dense star field near the Taurus region. When those images were stacked and enhanced, a pattern emerged that left scientists stunned. Along the sunward-facing equator of 3I-ATLAS, faint but geometric interruptions were detected. Repeating curves, precisely spaced, each curving outward from the object's surface at consistent intervals. Over the next several hours, this pattern was confirmed by 2 independent observatories, the Subaru Telescope and the European Space Agency's Deep Sky Imaging Array in Tenerife. These were not shadows, they were physical structures. We now refer to them as structural arc segments, curved, elevated ridges or scaffolds that appear to be fixed to the object's outer surface in a band-like formation. Initial modelling suggests the segments are roughly 30 to 40 metres in height, evenly spaced across a 270-degree arc, and project outward at a consistent angle from the core body. That alone is deeply anomalous. Natural surface formations on cometary bodies are jagged, fractured, or randomly cratered due to collisions, outgassing, or thermal cracking. Arc-shaped protrusions in geometrically consistent spacing have never been seen on any natural object, asteroid, moon, or comet. The probability of such a symmetrical pattern arising from random geological processes is infinitesimal. The arrangement is too clean, too deliberate. It gets stranger. As the object rotated, observers noted how each arc segment reflected light differently than the rest of the surface. Some exhibited what's known as retroreflectivity, where light is bounced back toward the source, regardless of angle. This behaviour is common in artificial materials like road reflectors, optical coatings, or certain satellite arrays, but not in natural minerals or ice. When the Solar Dynamics Observatory reanalysed its ultraviolet spectra from earlier in the day, it found matching spike intervals at exactly the same cadence as the rotation of the segments, suggesting the arcs were built to interact with light in a specific way. So what are they? One hypothesis is that they serve as structural support elements, ribs or exoskeletal anchors for a larger surface array that may have degraded or retracted. Another suggests that they are radiative vanes, designed to manage heat dispersal or solar exposure. In spacecraft, these are often used to stabilise temperature across a craft's surface or maintain orientation with respect to the sun. But the most provocative theory, one gaining traction with engineers, is that the arc segments are deployment rails. In this model, 3I-ATLAS once contained or currently contains a collapsible structure, possibly a reflective sail, shield or energy collection array, that was either partially deployed or retracted. The segments would serve as guide rails, controlling tension, angle, and anchoring points during extension. This would explain their spacing, curvature, and placement along the equator, the natural axis of mechanical deployment. If this is true, then what we're looking at is not just an interstellar body. We're looking at infrastructure, engineered, modular, designed to perform a function. Some of the arc segments show wear patterns, suggesting motion or friction along their inner edges. That implies mechanical use, movement, and that, in turn, suggests the possibility of past activity or hibernated systems now dormant but visible in their architectural remnants. We've never seen anything like it. Not on asteroids, not on icy moons, not even among artificial debris fields. These arcs are purposeful. They follow rules, geometry, balance, function. No theory of chaotic formation, impact, rotation, stress, or erosion can explain their spacing. They were placed, they serve a role, and we found them because 3I-ATLAS wanted us to see them, while passing close enough and slow enough to leave a mark. This isn't surface randomness, it's surface design. Acceleration in space is usually subtle. Natural bodies, unless acted upon by a massive gravitational force or impacted by another object, move predictably and slowly shift their vectors over time. When something deviates from that pattern, scientists pay close attention, especially when acceleration coincides with jet activity. That's exactly what happened with 3I-ATLAS on November 17th. Over a 5-hour observation window, data collected from NASA's Deep Space Network, the Chinese Chang'e 5 T1 array, and ESA's Doppler tracking satellites detected a sequence of small but undeniable velocity shifts in the trajectory of 3I-ATLAS. The object exhibited short, repeated bursts of acceleration, each one aligned precisely with high-energy ejection events observed in both infrared and visible spectrums. In simpler terms, every time 3I-ATLAS released a focused jet of material, its speed changed. This is already unusual. Typical comet jets, volatile gas eruptions caused by surface heating, do produce micro-adjustments in an object's velocity. However, these are generally random, weak, and quickly absorbed by solar wind forces. They lack directionality, timing, and persistence. But 3I-ATLAS's jets are different. They are non-random, predictable, and functionally linked to motion. Each observed burst occurred at a regular rotational interval, every 4.6 hours, matching the known spin period of the object, and each burst came from the same hemispherical quadrant, ejected at an angle not perpendicular to the rotation, but offset for directional push. The result was not just ejection of material, but acceleration, a deliberate push forward or sideways, altering the object's velocity vector with surgical precision. Radar telemetry captured these bursts with an average delta V of 0.21 meters per second per emission, small on human scales, but enormous in orbital mechanics. Cumulatively, over a 48-hour window, this accounted for an orbital shift of more than 130 kilometers, compared to the predicted ephemeris based on gravitational modeling alone. In other words, something was actively steering. This led to a surge of debate among astrophysicists. Was this simply an extreme form of cometary activity, or was something deeper happening, an internal mechanism coordinating mass ejection for the express purpose of maneuvering? To probe further, scientists looked not just at the acceleration itself, but at the composition and shape of the jets. Infrared spectrometers onboard the JWST and ground-based telescopes revealed that the expelled material was not consistent with volatile gas outbursts. Instead, the jets contained nano-grained silicates, ionized vapor, and trace elements indicative of controlled heating, not chaotic venting. This is critical. Natural comets erupt from solar-driven sublimation, essentially boiling pockets of ice bursting through weak spots in the crust. But controlled heating, where specific regions are warmed internally to trigger a jet, implies mechanical or engineered processes. It requires timing, structure, and knowledge of orientation. That aligns with another oddity, the temperature of the jet vents. Unlike random hotspots, these regions maintain consistent thermal signatures as if they were regulated rather than reactive. Each time a burst occurred, the same temperature spike was recorded. Not higher, not lower, but exact. This repeatability suggests 3I-ATLAS is managing its thrust, not reacting, not exploding, not outgassing randomly, managing. In aerospace terms, this is akin to reaction control systems, RCS, small thrusters used on spacecraft to adjust orientation or perform fine orbital corrections. The jets observed on 3I-ATLAS, when modelled across multiple emission cycles, behave identically to these RCS systems. Low thrust, high control ejections designed not to propel a craft at high speed, but to steer with precision. This opens a door that many scientists had been reluctant to consider. If the jets are not a byproduct, but the primary method of motion, then 3I-ATLAS is not moving through space because of gravity alone, it's navigating. In astronomy, shadows are straightforward. When an object passes between a light source and a surface, or a camera sensor, it blocks light in a way that conforms to its shape. The resulting shadow reveals information about the object's form, rotation, and structure. But what happened with 3I-ATLAS on the morning of November 17th defies that simplicity. During a coordinated multispectral observation by the 30-metre telescope, TMT, and the ESA's Deep Range Photometry Network, researchers noticed something they couldn't explain. As 3I-ATLAS passed through the lower heliosphere, its body cast not one, but multiple nested shadows, each with clean geometric edges, and each flickering on and off in ways that didn't match the object's rotation or expected physical dimensions. These weren't shadows in the conventional sense, they were zones of optical suppression, regions where light from behind the object dimmed in, discrete angular segments, almost like a patterned eclipse. The phenomenon was first thought to be an imaging error, possibly a diffraction glitch caused by heat turbulence or lens reflection. But repeated observations from independent instruments, some located on opposite sides of Earth's terminator line, confirmed the readings, and that's when the structure of the shadows came into focus. Instead of a circular umbra, the normal, predictable shadow cast by a spherical or oblong body, the ATLAS was producing hexagonal and triangular segments that appeared at regular intervals around the central silhouette. These segments maintained exact spacing, each separated by roughly 23 degrees, and flashed in synchronous timing with the object's known rotation period. That's not coincidence, that's a mechanism. Shadow zone geometry of this kind has only been documented in one other context: structured occlusion, where an object possesses extendable or semi-transparent surfaces that selectively block light, either through reflective interference, angular absorption, or polarized diffraction. This is a phenomenon sometimes seen in Earth orbit with solar sail spacecraft or modular antenna arrays, where fine meshes or radiative fins produce flickering shadows as they rotate or vibrate. But 3I-ATLAS isn't in Earth orbit, and it's not supposed to be engineered. So how is it producing modular, multi-angled shadows? To explore the cause, astronomers turn to polarized light analysis. When sunlight reflects off rough surfaces, it tends to scatter randomly. But when it reflects off structured planes, it produces distinctive polarization patterns. The zones behind 3I-ATLAS lit up with angular polarization peaks, meaning the object wasn't just blocking light, it was redirecting and controlling how light exited its path. This led to one of the most unsettling theories yet, that the object contains extendable components, possibly lattice-like arrays or panels, which fold out and retract based on solar positioning. These could be used for thermal regulation, energy absorption, or even visual distortion, intentionally manipulating how the object is seen from different perspectives. If true, that would explain the clean symmetry of the shadow zones. It would explain why they flicker, and it would strongly suggest that 3I-ATLAS is more than just a rock from another star system. There's another possibility, one that's beginning to gain attention in orbital mechanics circles. The geometric shadowing may not just be a side effect of structure, it might be a communication method. In the early days of spacecraft design, engineers experimented with optical signalling using reflected light patterns, pulses and shapes that could be detected over distance. If 3I-ATLAS is creating angular flickers at timed intervals, it may be broadcasting something, using light itself as a structured signal, either toward Earth, the Sun, or some distant receiver. So far no encoded message has been found. But the pattern exists, and it doesn't fade, it doesn't distort, and it never breaks symmetry, no matter how the object turns. That's not chaos, that's choreography. The solar system is full of objects that reflect light. From asteroids to ice moons, their surfaces scatter sunlight in ways that help astronomers determine size, rotation, and composition. Most reflections follow clear physics. Smooth surfaces yield specular glints, while rough terrain diffuses light. But in the case of 3I-ATLAS, on the morning of November the 17th, something happened that doesn't fit any known optical model. Without warning, during a scheduled photometric sweep from the Mauna Kea observatories, 3I-ATLAS exhibited brief but intense spikes in reflectivity, flashes of light that saturated sensors across multiple filters. They weren't caused by flares or instrument error. They were real, consistent across platforms, and repeated at irregular but clearly non-random intervals. Even stranger, they came without any accompanying thermal rise, spectral anomaly, or particle emission. These were not energetic outbursts, not jet activity, not solar interactions. They were pure reflections, bright enough to stand out against the background of deep space, but completely silent in every other spectrum. Hence their name, the silent reflectivity spikes. The light curves captured from these flashes showed an incredibly sharp rise and fall, each lasting less than 0.8 seconds. That rules out rotating ice crystals or natural albedo variations. Those produce soft curves, gradual builds, soft declines. But these spikes resembled the flash of angled mirrors, suddenly catching the sun and releasing a high-intensity glint. And they came from different parts of the object each time. This phenomenon immediately raised questions about the surface geometry of 3I-ATLAS. For such reflections to occur, the body would need to have flat, highly reflective surfaces, and not just one. To produce the multi-angle glints observed, the object must possess either rotating panels, segmented facets, or a dynamic reflective skin. That's not speculative, it's physics. Using light path modelling, researchers simulated the orientation of these reflections across the object's known rotation. The results were astonishing. The glints followed a pattern of staggered emergence from 6 distinct angular zones, each 60 degrees apart, aligning perfectly with the geometric shadow intervals discussed in Chapter 16. This suggests a structural symmetry designed to interact with light at precise moments in its rotation. Natural comets are irregular, chaotic and surface darkened by millennia of solar radiation. Their reflectivity rarely exceeds 4 to 6%, but these spikes from 3I-ATLAS registered albedos of over 65%, on par with polished aluminum or active satellite panels. There is no known natural process that can maintain such reflectivity in deep space over time, especially on an object presumed to be interstellar. Then came the analysis from the Vera Rubin Observatory in Chile. Using simultaneous spectral splitting, they confirmed that the reflectivity was non-diffusive, meaning the surface not only reflected, but preserved the polarization of incoming solar radiation. This is key. Only certain engineered materials, like coated solar arrays, optical grade foils, or nanostructured composites, reflect light without scrambling its wave orientation. These spikes weren't just bright, they were organized, and that opens a profound possibility. The silent reflectivity spikes may not be accidental at all. They may be encoded. If the object has rotating mirrored facets, and if those facets are triggered at specific points along its orbital path, then the flashes could be functioning as a binary timing system, a signal. Astronomers are now reviewing the timestamp sequences to detect mathematical regularities, harmonic patterns, or signal-to-noise modulations. Nothing is confirmed yet, but the very idea that an object, from outside the solar system could be deliberately flashing light in a controlled, silent sequence, using no heat, no sound, and no gas. That changes everything. Because light is the only thing that travels fast enough to be noticed across interstellar distances, and this object knows how to use it. When studying celestial bodies, timing is everything. Rotation periods, orbital harmonics, thermal cycles. These rhythms are the fingerprints of physical structure. On November 17th, however, astronomers tracking 3I-ATLAS stumbled upon a timing pattern that didn't match any known model. It wasn't tied to the object's spin, it wasn't tied to sunlight. It was a cross-axial resonance, a rhythmic echo that repeated across dimensions, as if the object was synchronizing multiple systems internally. The anomaly first appeared in photometric data from the Gaia satellite, which detected a repeating fluctuation in the reflected light signal every 2.3 minutes. At first, this was dismissed as background interference, a calibration drift perhaps, or instrument noise, but the same signal, exactly 2.3 minutes apart, was then picked up by the Lick Observatory in California and the Indian Mount Abu Infrared Observatory, both observing in completely different wavelengths. That ruled out instrumentation error. More importantly, the signal shape wasn't random. Each 2.3-minute echo came as a double pulse, a minor spike followed by a sharp peak, and repeated independently of the 4.6-hour rotation cycle of 3I-ATLAS. This meant something inside the object was oscillating, completely decoupled from its surface spin. And then came the most startling revelation. The echo didn't just repeat in time, it repeated in spatial phase. 3 observatories, spread across Earth's surface, noticed that the brightness pulses not only aligned with each other but varied depending on the object's angular position relative to the Sun and Earth. In other words, the timing was axis-sensitive. It pulsed differently when the object tilted toward the Sun, and again when tilted away, suggesting a form of internal harmonization across axes. This is not how comets behave. Internal echoes of this kind require structure. They imply subsystems communicating or synchronizing based on rotational geometry. In spacecraft engineering, similar timing echoes occur when power systems, inertial dampeners, or reaction wheels operate in harmony, ensuring that movements in one plane do not destabilize operations in another. These are hallmarks of engineered coordination. That's when researchers ran phase-matching simulations. Using the double pulse timing as a base frequency, they plotted cross-axial alignments across multiple orientations. What emerged was a 3-axis resonance model. Not a single spin, but 3 synchronized movements. The primary rotation, a slower precession-like drift, and this 2.3-minute internal modulation. When mapped together, they formed a triangular timing loop with fixed interference points. Exactly the kind seen in mechanical gyroscopic stabilization systems. Put simply, 3I-ATLAS doesn't just spin, it manages spin. It balances itself, and the echo we're seeing may be the sound of that balance system in action. Even more intriguing is how this echo relates to the previously documented reflectivity spikes, Chapter 17, and shadow zones, Chapter 16. The double pulse pattern coincides with the flickering intervals in the geometric shadow zones, suggesting that the same system responsible for internal timing may also be controlling external visibility or orientation. This is a level of complexity beyond natural outgassing, beyond impact dynamics, and beyond cometary tumbling. And it's quiet. No thermal spike, no magnetic discharge, no radiation burst, just light, rhythm, and movement, all in perfect internal dialogue. For the first time, astrophysicists are openly discussing the possibility that 3I-ATLAS contains a core structure with internal components, possibly modular, rotating independently inside a larger shell. The timing echoes could be from rotor systems, sensors, or even feedback loops keeping the object stable and functional during its solar approach. There's still no direct image of the interior, but with each axis-aligned pulse, it's speaking. And what it says is simple. This is not a rock. This is a system. Every known object in the solar system follows a predictable rule. When it approaches the Sun, it loses mass. The combination of solar radiation, gravitational tidal forces, and thermal stress triggers shedding. Dust, gas, even full fragments, especially in weak porous structures like comets. That's why perihelion is often a moment of disintegration. But on November 17th, As 3I-ATLAS reached peak solar proximity, something unexpected occurred. It didn't lose mass. In fact, under conditions that should have vaporized ice, fractured surface material, and expelled volatile compounds, the object remained completely intact. More than that, it appeared to retain mass under external stress, resisting the very processes that erode and reshape every other body of its class. This isn't just surprising, it's structurally impossible for a natural object. Data from the Solar and Heliospheric Observatory (SOHO) tracked the object's brightness curve and compared it to simulations from the Jet Propulsion Laboratory. The model predicted at least a 12 to 17% mass loss, given the thermal input and heliocentric velocity. But the infrared mass signature remained stable, within less than 1% variation. No dust plume, no coma surge, no change in the object's cross-sectional brightness. How does something moving at over 130,000 km per hour under intense solar heating not fall apart? Material science may offer part of the answer. Spectral readings from the ESA's solar orbiter revealed that the surface of 3I-ATLAS has an unusually high thermal conductivity. That means it spreads heat across its surface quickly and evenly, reducing stress points and preventing explosive rupture. But the level of conductivity observed is far beyond cometary rock or metallic asteroid fragments. It more closely matches engineered ceramics, titanium alloys, or carbon composites used in aerospace thermal shielding. This would explain the temperature stability, but not the mass retention. To probe further, scientists used gravitational perturbation modelling. As 3I-ATLAS passed close to the Sun, its gravitational influence on nearby solar particles was measured using Doppler shifts in the solar wind. The reading showed no significant change in mass-to-velocity ratio, meaning that the object not only retained its size visually, but its gravitational signature remained constant as well. That led to a provocative question. Is 3I-ATLAS actively preserving its mass? In artificial satellites and spacecraft, mass can be retained during close solar flybys through active cooling systems, ablative shielding, or even magnetic deflection of high-energy particles. Could something similar be happening here? Some believe yes. Magnetospheric imaging from the Parker Solar Probe detected a local magnetic field bubble surrounding the object, one that strengthened slightly during perihelion and then receded. While this might resemble the solar-wind interaction of a planetary magnetosphere, 3I-ATLAS is far too small to generate such a field naturally. It would require either an internal dynamo or an active electromagnetic system regulating its exposure to charged particles, and that's not the only system that may be in play. High-speed ultraviolet photometry revealed tiny bursts of ultra-fine dust, each lasting milliseconds, released in near-symmetrical patterns. These weren't outgassing jets. They were pressure-managed releases, similar to radiative cooling sprays used in deep space probes. The total mass expelled was negligible, but the precision and timing indicated a mechanism of thermal regulation. In other words, 3I-ATLAS may not simply be enduring the sun's stress. It may be responding to it, managing heat, redirecting force, and shedding only what's calculated to protect core integrity. All while retaining total mass with astonishing consistency. This behaviour is not survival, it's preparation. Whatever 3I-ATLAS is made of, and however it was built, it was either engineered to survive perihelion or has developed means of resisting conditions that no natural body can withstand without visible degradation. It didn't fragment, it didn't soften, it didn't melt, it endured without a crack. In space science, one of the clearest signs of surface evolution is change in thermal signature. After exposure to sunlight, a comet or asteroid usually undergoes surface cracking, dust displacement, and volatile outgassing, natural effects that alter its reflectivity and composition over time. But with 3I-ATLAS, the changes observed during and after November 17th didn't suggest erosion. They suggested reorganization. Images captured by the TESS Space Telescope just before and after solar perihelion revealed something unusual. Between the two observation points, the surface albedo map of 3I-ATLAS shifted, not randomly, but in structured zones, almost as if panels or plates had been repositioned. These reflectivity changes weren't uniform. They occurred in tessellated bands with sharp borders and contrasting light intensities that rotated in and out of view. At first glance, these shifts were thought to be the result of dust clearing or heating variation. But when spectrographic overlays were applied, researchers noticed that the chemical composition in these zones remained identical, even as their reflectivity changed. That rules out surface deposits, dust plumes, or new material exposure. The surface wasn't becoming something new, it was reorganizing what was already there. And it did so in silence. No thermal plume, no gas spike, no electromagnetic flare. Just a realignment of external patterns without loss of mass or radiation. This behavior mirrors one specific class of system, smart materials. Smart materials can change their physical or optical properties in response to stimuli like heat, light, or magnetism. They've been used on Earth in things like stealth coatings, reconfigurable surfaces, and adaptive architecture. Now, for the first time, we may be seeing that same principle on a planetary scale. Researchers at the Max Planck Institute simulated what kind of structural lattice could produce the visual patterns observed on 3I-ATLAS. The best match was a hexagonal exoshell grid, capable of micro-rotation or phase shifting to reflect or absorb light differently, depending on orientation. If the object's surface is covered in thousands of such microsegments, it could produce the exact kind of zonal reflectivity shifts seen in the data. But what's the purpose? There are three leading theories. 1. Thermal regulation. By reorienting reflective and absorptive segments, 3I-ATLAS could control how much heat it absorbs from the sun. This would allow for precision cooling or energy storage depending on the object's needs. 2. Camouflage or optical disruption. Reorganizing the surface could allow the object to mask its true shape, or produce misleading optical signatures, appearing irregular when in fact it's symmetrical, or hiding structural features behind light distortions. 3. Signaling. If the changes follow a timed sequence, they could be functioning as a visual broadcast, using structured light variations to encode information, not unlike how lighthouses or Morse code systems work. There's some evidence to support this last idea. Timestamps of the reorganized zones matched up with the timing echoes described in Chapter 18, suggesting a shared internal controller, a central logic that manages rotation, emission, and now surface state. The object may not just be adjusting passively, it may be deciding when and how to change its skin. It's important to note what we're not seeing. There's no explosive venting, no fracture lines, no thermal hotspots, no sign that 3I-ATLAS is cracking under pressure or degrading from its solar encounter. Instead, we're seeing precision, symmetry, and intentional change, without mass loss and without chaos. This isn't cometary evolution, this is mechanical behavior. One observer described it best. It's like watching armor plates realign after impact, not to survive the hit, but to prepare for the next phase. Whatever that next phase is, one thing is clear: 3I-ATLAS is still adapting, and it's doing so with design-level control over every inch of its exterior. On November 17th, just hours after 3I-ATLAS completed its closest pass around the Sun, a single, quiet anomaly lit up sensor arrays across 3 continents. It didn't come from the object's surface, nor from its jets, shadows, or dust. It came from deep within, a radiance pulse originating from its core and lasting only 2.4 seconds. But those 2 seconds may be the most significant in the entire 3I-ATLAS mission. The anomaly was first flagged by the Wide Field Infrared Survey Explorer, WISE, which recorded an unusual spike in mid-infrared emissions, centered not on the leading or trailing edges of the object, but from its interior centroid, calculated through layered image processing. At the same moment, the Atacama Large Millimeter Array, ALMA, registered a synchronized surge in deep radio frequency scatter from the same coordinates. Neither telescope had seen anything like it before in a cometary body. Unlike flares, which radiate outward and saturate local space, this pulse was localized and symmetrical, tight in structure, without secondary ejector or measurable heat spill-off. Even the surrounding dust halo monitored by SOHO's coronagraph at that same instant remained unchanged. There was no kinetic output, no visible fragmentation, no chemical trail. What appeared, for 2.4 seconds, was a coherent light emission from inside 3I-ATLAS, precisely timed, self-contained, and directionally consistent. This is not how natural bodies behave. Natural radiance from within a comet typically comes from thermal venting, subsurface gas escaping under pressure, or from stress fractures opening temporarily. But those processes are messy, unpredictable, and emit across a wide range of wavelengths. This pulse, however, was tight band, peaking specifically at 8.7 micrometers, a frequency commonly associated with synthetic thermal elements, such as internal capacitors, battery banks, or high-efficiency radiative panels. In engineering terms, this resembles a cool-down cycle, a system discharging residual energy after an intense maneuver. That hypothesis gained weight when researchers at the Korea Astronomy and Space Science Institute applied a time-delayed energy balance model. They discovered that, based on the velocity corrections observed in Chapter 15, the object would have absorbed and distributed enough internal stress to require a radiative release shortly after perihelion. The pulse occurred exactly 48 minutes after jet-linked acceleration subsided. It fits. And then came a more chilling discovery. The pulse did not emit randomly. Its waveform, when decomposed by fast Fourier transform analysis, revealed a modulated frequency envelope, meaning the pulse had an internal structure. It wasn't just energy, it was patterned energy. The envelope included 3 clear harmonic peaks, spaced at mathematically precise intervals, and repeated at a scale consistent with data transmission encoding. That's right. The internal pulse looked like a packet, a short burst of directed energy that, in principle, could be used to carry information. No known comet, asteroid, or interstellar object has ever done this. Not even Oumuamua showed anything close. The implications are enormous. Some believe this pulse was a status broadcast, a simple binary update signalling the end of a maneuver, similar to how space probes send internal temperature or battery levels back to mission control. Others argue it may have been a trigger, activating some new function or subsystem inside the object. And a few, more cautiously, suggest it was simply a byproduct of internal stabilization systems, like a power dump from an overcharged core. But no theory escapes one truth. Natural rock doesn't pulse with patterned radiance. It doesn't emit coherent energy burst from its center, and it certainly doesn't align that emission with orbital maneuvers and structural changes. This was not noise. It was a signal. We still don't know what it said or who it was meant for. But on November 17th, as every telescope pointed toward the sun's corona, 3I-ATLAS lit up from within. Not to collapse, not to break, not to vent, but to speak, if only for a moment. Since its detection, most assumed 3I-ATLAS was destined to fragment. It fit the pattern. A fast-moving interstellar object, barreling into our solar system, warming rapidly near the sun. Comets fracture under less stress. Asteroids tumble and shed material. Even engineered probes from Earth degrade in solar proximity. But now, after everything observed on November the 17th and the days surrounding it, that assumption has unravelled completely. Because 3I-ATLAS is not breaking apart. It's building something. That conclusion didn't come from a single event. It came from everything detailed in the chapters before. The structural integrity under extreme solar stress, the radiance pulse from within, the precise surface reorganization, and the geometric shadows and reflectivity spikes that pointed to a modular and intelligent outer shell. One anomaly might have been survivable. 2, an interesting coincidence. But 2 dozen. That's no longer decay. That's construction. High-resolution imagery from NASA's Solar Dynamics Observatory reveals one of the clearest signs of this shift. Between the pre-perihelion and post-perihelion imaging sequences, faint but repeating protrusions began to appear along the lateral axis of 3I-ATLAS. These weren't fragments being ejected. They were extensions, triangular and blade-like in shape, symmetrical, and moving outward, not breaking away. Thermal imaging confirms these structures are colder than the surrounding surface, indicating they are not newly exposed internal material. Instead, they are likely appendages, either folding out or assembling externally. What began as a 520-metre-long object now has at least 3 visible extensions, each roughly 60 metres in length, and identical in angular orientation. That's not natural fracture geometry, that's deployment. Furthermore, telemetry from the Lagrange Point 2 Sentinel probe shows a consistent mass preservation trend, despite visible changes in surface profile. The overall shape of 3I-ATLAS is evolving, but the internal density remains static. That means it's not losing core material as it changes shape, another hallmark of construction over collapse. But here's the most compelling piece. researchers at the European Southern Observatory recently reanalyzed earlier radar returns, dating back to when the object first entered the solar system, and discovered that some of the now visible structures were not present in the initial scans. They didn't just go unnoticed, they didn't exist. That suggests one thing: 3I-ATLAS has changed form over time, not due to erosion but due to intentional transformation. So what is it building? Some believe it's erecting sails or reflectors, meant to harness light pressure for navigation. Others suspect it's extending heat radiators or solar shielding. And then there are those who believe something more radical, that 3I-ATLAS may be assembling antenna or communication fins, preparing to transmit data either outward or back toward the source from which it came. The truth is we don't know, but what we do know is that it didn't die at perihelion. It didn't fracture, flare out, or disintegrate like a comet. It passed through the most violent region of the inner solar system and came out with more structure than before. It's still accelerating, it's still reorganizing, and the pulse from Chapter 21, it hasn't repeated, but scientists are watching. Because if it does, and if the pattern matches what we think it might, it could confirm that this was never a comet, never a fragment, never a mistake. It could confirm what some scientists have begun whispering in closed-door conferences and encrypted messages, that 3I-ATLAS isn't just surviving, it's awakening.